One. In this video, we are going to be looking at chemical equilibrium, basically Lechatelier principle and the factors that affect equilibrium position. Now we start with what a reversible reaction is. Okay, a reversible reaction is one that can proceed in both forward and reverse direction, written in the form AA plus BB, giving us CC plus DD. Now I want to note that this arrow, which is basically written this way, okay, signifies that the reactant can give rise to product, and the product can also give rise to the reactant. That means reactants can combine to give product, and products can also combine to give reactant. Okay, an example is the Haber process. That's the Haber process, where you have nitrogen gas combining with hydrogen gas to give us ammonia gas. Is an example of a reversible reaction. Nitrogen gas plus adding with hydrogen gas is going to combine to give us ammonia. In the same way, ammonia can dissociate to give us back nitrogen and hydrogen. Okay, that leads us to the next, which is dynamic equilibrium. Now, a system is said to be in dynamic equilibrium, which is also, in this case now, chemical equilibrium. Okay, so we can say chemical equilibrium is an example of dynamic equilibrium. Now, I start all over. A system is said to be in dynamic equilibrium if the rate of the forward reaction is equal to the rate of the reverse reaction. Now, it is worthy to note that chemical equilibrium is only possible in a closed system with no loss in mass. So a closed system is actually a system that where there is no loss in mass, but there is loss in matter. Now, I would like to point here that there are three types of system. We have the open system. Now, when you say a system is open, it means that it can lose mass, it can lose matter, it can also lose energy. It's open. A good example is cooking with your pot open. The second type of system is called, what we just looked at now, is called a closed system. A good example is cooking with your pot closed. In that case, your matter can be lost, but energy cannot be lost. I mean, energy can be lost, but matter is not lost. That means there is no loss in mass, there is no loss in matter, but there is loss in energy. Then the third type of system is called the isolated system. Now, for the isolated system has to do with a sealed system. Isolated, there is no loss in mass, no loss in energy. It's completely sealed, where there is no interaction at all with the surrounding. Okay. Now, that leads us to Lechatelier principle. Okay. This principle states that when a system in equilibrium is influenced by an external constraint, the equilibrium position will shift in order to annul the effect of the external constraint. Okay, so that means that your equilibrium reaction, whatever it is, can shift to the right and also shift to the left. This is the right and this is the left. So it is possible. There are certain factors that when imposed on this very equilibrium position, the position will either shift to the right or will shift to the left, depending on the factor. So if I'm interested in producing this, it means that I will need to know how to manipulate the factors in order for this particular reaction to favor the forward reaction, the same way with that of the reverse. Now let's see, what are these factors that affect equilibrium position? The first one of them is concentration. The second is pressure or volume, pressure and volume, because they are inversely proportional. And the third is temperature. Okay, so please take note of this. Take note that the presence of or absence of catalyst does not affect equilibrium position. So catalyst does not affect equilibrium position. Please take note. Now let's see, how does concentration affect equilibrium position? Now, increase in concentration of the reactant side. Remember, this is the reactant side. and this is the product side. Okay, so when I increase the concentration of the reactant, it's going to favor the formation of the product. Another way of saying that is that it's going to favor the forward reaction. That means more of this reaction, more of this product will be formed. When I increase the concentration of the reactant, it means it will favor the forward reaction. In the same way, vice versa, if I decrease the concentration of the reactant, it will favor the backward reaction. That's the same. In the same way, increase in concentration of the product favor the formation of the reactant. That means the backward. So if I have my reactant and have product, and I increase the concentration of this product, it is going to favor the backward reaction, and vice versa, meaning that if I decrease the concentration, it will favor the forward reaction. Okay, let's note some other things here. Now look at this example, AABB giving us CCDD. Increase in concentration of A or B. So if A or B is increased, will shift the equilibrium position to the right. That means favor the forward reaction. But decrease will shift the equilibrium position to the left. That means favor backward reaction. So, okay, then consequently, increase in concentration of C or D, that's any of the products, will shift the equilibrium position to the left. That means favor the backward reaction, but decrease of any of C or D will shift the equilibrium position to the left. So what are we saying? In other words, if I want to make this reaction to favor the forward reaction, there are two things I can do. It is either I increase the concentration of the reactant or I decrease the concentration of the product. I take that again. If I want the equilibrium position to shift to the right, that means more of the product is formed. Then I will either decrease the concentration of the product or increase the concentration of the reactant. In the same way, if I want the reactant to be favored, that means I want the equilibrium position to shift to the left. It means I will either increase the concentration of the product, which is C or D, or I decrease the concentration of the reactant. Please take note. Okay, now let's see this question. It says, consider the reaction, nitrogen gas combining with hydrogen gas to give us ammonia. What do we do to the concentration for more of ammonia to be formed? Okay, good. It is either we increase any of the concentration of nitrogen or hydrogen, or we decrease the concentration of ammonia. I hope we understand that. Now let's look at effect of pressure on equilibrium position. Now, increase in pressure will favor the side that has the lowest number of moles, and vice versa. And we should note this, only gases and aqueous solutions are considered. We only consider gases and aqueous solution. Now look at a very good example, 2SO2 combining with O2, giving us 2SO3. Now, whenever I want to find out how pressure affects the equilibrium position, all I do is I will add the number of moles. The number of moles of SO2 here is 2. The number of moles of oxygen here is 1, making it all together 3 moles, 3. Now, but coming to the right-hand side, which is the product side, the number of moles of SO3 is just 2. So SO3, the right-hand side has just 2 moles, but the left-hand side has 3 moles. So what do we say here? That the increase in pressure of the system will shift the equilibrium position to the left. Why? Because the left has the lowest number of moles. 2 moles is lower than 3, is lower than 3 moles. I should use the sign. Okay, good. Now, let's see more examples here. We have hydrogen plus iodine gas giving us 2Hi, and we are asked in the reaction above, the pressure, we are told the reaction above pressure has no effect since the number of moles of the product is equal to the number of moles of the reactant. We can see that the number of moles of hydrogen here is 1. The number of moles of iodine here is 1. The number of moles of Hi here is 2. So if I add that of hydrogen and iodine, I'm going to get 2. So left hand side is 2, right hand side is 2, making it equal. What does that mean? Pressure has no effect because both sides have the same number of moles. Now let's look at effect of temperature on equilibrium position. Okay, now for an endothermic reaction, that means how do you know an endothermic reaction? Delta H is positive. Another way you can say that is that delta H is greater than 0. So once delta H is greater than 0, or you say positive, is an endothermic reaction. Increase in temperature will favor the forward reaction. As long as the reaction is endothermic, increase in temperature will favor the forward reaction and vice versa. Now, for an exothermic reaction, delta H is negative. That means delta H negative, or you say delta H is less than 0. This is for an exothermic reaction. Increase in temperature will favor the backward reaction and vice versa. What that means is that if I decrease the temperature, it will favor the forward reaction. So once I'm dealing with temperature, then the two questions I ask myself, is the reaction an endothermic reaction or an exothermic reaction? If I confirm it's an endothermic reaction, I know that increase in temperature will favor the forward reaction, but decrease in temperature will favor the backward reaction. If I know that it is exothermic, then increase in temperature will favor the backward reaction, but decrease in temperature will favor the forward reaction. Okay, let's see this example here, 2SO2 plus O2 giving us 2SO3. Now, you can notice here, we are given something here, which is the enthalpy change, and it is minus 198 kilojoules per mole. Now, for the reaction above, that should be above, increase in temperature will favor the reverse direction since it is not endothermic. That's a mistake. It's an exothermic reaction. Why is it exothermic? Because delta H here is negative, so increase in temperature must favor the reverse direction. Thank you very much.